Good morning and welcome to our first DryFiciency webinar. My name is Veronika Wilk. I work for the Austrian Institute of Technology in Vienna and I'm the scientific coordinator of the DryFiciency project. And it's a great pleasure for me to guide you through this webinar today. It's the first of a short series of webinars where we will present the insights and the results of the DryFiciency project. And today we will start with the core components that are needed for high temperature heat pumps. But before we go into the details on the component development, I will give you a brief overview on the project itself. So the DryFiciency project is an EU-funded project, a Horizon 2020 project. We started with this work in September 2016, and it's almost 5 years ago. And we are about to finish now, and this is why we started with this webinar series on the results. The aim of the project is to develop and to demonstrate high temperature heat pumps for industrial applications that are able to reach 160 degrees C of heat supply temperature. And in this project, we are 13 partners. And I will present all of them to you now. So we have 2 research and technology organizations. It's AIT and SINTEF. We have 5 component manufacturers that you're going to meet today. This is Bitzer, Rodrex and Heaton, Chemours and Fuchs. We have an expert in system integration in our team, EPCON, and our 3 end users where the heat pumps are located and operating. This is Agrana, Wienerberger and Scanship. And then we have 2 dissemination partners, RTDS and the European Heat Pump Association, EHPA. The focus of our project are drying processes, because these processes are widespread in a number of industries and they use lots of fossil fuels for their energy supply. And they also generate large volumes of low-grade waste heat. So drying processes are a perfect application for high temperature heat pump. And with the introduction of this advanced energy efficiency technology, we aim to improve the energy efficiency of the process and to considerably reduce the carbon emission. And this should also contribute to the competitiveness of the industry. And this slide is basically a visual summary of our results on the project. The cornerstone of the project is the industrial demonstration. So we have designed and built and integrated 3 high temperature heat pumps in different processes. In the project, we worked on 2 different heat pump designs, 2 closed loop heat pumps for air drying and an open loop heat pump for steam drying. And in the pictures from left to right, we have the different demonstrators. So the red container is integrated in a brick factory of Wienerberger, the world's largest brick producer. And there the closed loop heat pump supplies hot air for drying. In the middle, we see the demonstrator that is located at Agrana, an Austrian food company. And they have a closed loop heat pump that supplies heat for starch drying. And on the right, that's the open loop heat pump system that supplies steam for a sludge drying process. And this demonstrator is located in Norway in Drammen and is operated by Scanship. That said, this is the first webinar of our series. Today, it's about the core components. And in 2 weeks' time, you will have the opportunity to learn more about our demonstrators. So it's Wednesday, the 21st of April. Then you can meet our end users, Agrana, Wienerberger and Scanship, and learn about their experience. And the end of that series is our final conference that will take place also online on the 6th of July. And I kindly invite you to join us at this event as well. So what's up for today? We will have 5 presentations on the core components that are used for the DryFiciency demonstrators, followed by a virtual roundtable discussion. And I kindly invite you to engage with us, to participate in the discussion and to post your questions in the chat box. And we will come back to your questions then in the roundtable discussion. And you find the chat box in the lower part of your Zoom window. And now I would like to introduce our speakers. We will start with a presentation by Dennis Eber. He's an R&D engineer for refrigeration oils at Fuchs in Mannheim in Germany. And he started to work at Fuchs in 2008 and developed almost all the refrigeration oils that are available at Fuchs. The second presentation will be given by Lloyd Giroux. He is the heat pump and air conditioning business development lead for low GWP refrigerants at Chemours, and he has over 20 years of experience in the chemical industry. And he's an expert on how to use low GWP refrigerants in air conditioning and heat pump systems, also considering the performance and redesign as an alternative for the traditional HFCs. And then we will have 3 presentations focusing on different types of compressors. And the first one will be given by Julian Pfaffel. He's working for Bitzer for 15 years, and he is responsible for the product performance department, which is generating performance data for compressors and condensing units. And they also develop software simulation models and digital documentation. And he's chairing the ASACOM certification program for compressors and condensing units since 2012. The second compressor presentation will be given by Søren Schmidt, and he's working at Roadtrax, where he began his professional career as an engineering student in 2008. And since then, he has had several roles within the company, primarily around product development and also management as a lead engineer. Today, he's the head of operations and the project leader for the DryFiciency activities. And last but not least, we will hear a presentation by Geir Ropstad. He is the COO and founder and partner of Heat and AS, a company that has developed a high temperature heat pump and is also supplying one of the compressors that is used in the DryFiciency project. His experience ranges from international technical top management in renewable energy to establishing new businesses in Norway and abroad. And he has also experience in the participation of international management teams and large EU-funded projects. So, and with that having said, I'd like to hand over to Dennis, and I will stop my screen now, and please ask your screen, and we look forward to your presentation.
So thank you, Veronica, for your introduction. And I tell you something about the lubricant development in the DryFiciency project. Our task in the project was to develop lubricants for high temperature heat pumps with the refrigerant DR2 or R1336 MZZZ for a screw and a reciprocating compressor. The conditions are very hard for the lubricant. We have a high temperature and a high pressure in the system. This leads to a strong dilution by the working fluid, and the high temperature decreases the lubricant viscosity. So we looked at different raw material base oils which could be used for the system. And we looked at polyalpha olefins, we looked at polyolefins, we looked at complex esters, and we also looked at PAG lubricants, polyalkylene glycol products. And they looked the most promising because the miscibility is quite good with the refrigerant. They have a good viscosity index and a high film strength at elevated temperatures. And they have a quite good thermostability with the DR2 with an optimized additive system. The first info I want to tell you and show you is the miscibility gap. You can see here the diagram, which is shown here, which shows the concentration of the oil. So here on the left side, we have zero oil in the mixture with the refrigerant, and on the right side, we have the pure lubricant. And what you can see here, this white space and the gray space is the space of the good miscibility, where the oil and the refrigerant DR2 is creating only one phase. So the oil and the refrigerant are miscible. And then we have here in the yellow space, the room of the miscibility gap. In the miscibility gap, we have 2 phases. We have on upper phase, we have the lubricant, and the lower phase is created by the refrigerant DR2. And you see the miscibility gap is very small. And here, at low concentrations of the oil, the miscibility is giving. And so the lubricant is transported back to the compressor to safely lubricate the compressors. Then the next thing we did is this pressure, viscosity, temperature measurement. You see here in the diagram, you see the temperature, which is given here of the different systems. And then you see the blue lines is the pressure. And then you can read on the left side the kinematic viscosity of the lubricant. And so we have two compressor types. So we have the pizza compressor, which needs a minimum viscosity of about 6 centistokes. And the compressor has the parameters, the working parameters of 155 degrees Celsius, which is this line at 18 bars. This is here between the two blue lines, and you see we have a kinematic viscosity of 9 centistokes. And so the product here, this is the PHG with 680 centistoke product, has enough viscosity to lubricate a screw compressor. And then we have the Viking reciprocating compressor, which has 104 degrees and 4 to 4.1 bars at the suction side. And here's again the same. We look at the temperature, 104 degrees Celsius, and the pressure here, we have these 4 bars, and the viscosity is about 40 centistokes. So we have a lot of enough viscosity to lubricate this machine safely. And as you can see, one oil can be used for both applications. The next topic we had in the development of the lubricant for the DryF project was the seal tube test or the aging stability test. We did this test with different PHG lubricants with different additive system and the DR2. And we tried to optimize the thermal chemical stability of the lubricant with the DR2. And we tested different additive systems and analyzed the oil after the test via total acid number measurement and the chromatography determination. So what is done at this test? We put into a glass tube, we put iron, copper, and aluminium. Then we put in the refrigerant and the oil, and then we age it for 2 weeks at 175 degrees Celsius and look after. And the tubes here, as you can see in the picture, are frozen and sealed. And then after the 2 weeks, we open it up and then we make the total acid number measurement and the ion chromatography to see how much decomposition is happening. And then I show you that we did numerous tests with different PHG lubricants with different additive systems. And we looked here and found that the additive system 197 has the best total acid number increase from 0.07 to 0.38 and is creating a low amount of ions here in this test. So our final product we developed is a PHG product with the additive system of 197. It has a kinematic viscosity of about 600 centistokes at 40 degrees Celsius. At 100 degrees Celsius, we have 94.5. The viscosity index is 250, is very high. The total acid number of the fresh oil is very low, very good. The pour point, or the point where the oil stops flowing, is minus 36 degrees Celsius, so it's also very good. The density is 0.997 gram per milliliters. The flash point is 220 degrees Celsius, and the color is very light and clear. So the performance of the lubricant with the DR2 is very good. We have the good miscibility, we have a good lubrication performance, and we have a good thermal and chemical stability of the lubricant, which was developed for the DryF project. So this was my presentation, and I thank you for your attention and wait for your questions.
Thank you very much for the presentation and also for the impressive work that you've done in the DryFiciency project. And now I would like to hand over to Loic Chauveau, who will give us an insight into the refrigerant.
Thank you, Veronica. I will now present you the refrigerant that was presented by Dennis as a DR2, which is the molecule HFO 1336MZZZ, which is the isomer. And in the presentation of Dennis, you've heard about the DR2, which was the developmental reference that we have been using for that molecule. At the time we started the DryFiciency project, because at that time it was still a product that was not commercial and we didn't have any asset. And now, let's say, 5 years later, we have that product commercial, which is under the name Opteon MZ, and we have also much more experience on how this product is performing in this high temperature waste heat recovery applications such as the DryFiciency project. And I'm going to share with you some of the reason of this refrigerant development with regard to the regulation we have been following when we have been designing that product, but also presenting with you later some of the key characteristics of that refrigerant that you can somehow consider that are enabling the very high temperature heat pump application that have been developing by the DryFiciency project. Now, back on the regulation, which is really the essence of the low GWP refrigerant that we've been designing with the 1336 MZZ molecule. We are following the phase down of the F-gas regulation that have been put in place in Europe based on different amendment and protocol that I'm sure you have heard about, the Kigali amendment, the Kyoto protocol to reduce the average GWP number of the refrigerant that are used in a lot of different refrigerant systems and heat pump systems, and looking at the GWP number of the product that were somehow in the scope of being commercial at the time this project started, so kind of 5 years earlier. We had only one product that was really used so far for high temperature heat pump, even though again at that time there was no real commercial solution that could be considered for such a very high heat supply that have been the objective of this DryFiciency project for heat supply at 160 degrees C. At that time, so again, 5 years earlier, so in 2015, we had, the refrigerant 245FA that was, and that is still a product, used for high temperature application, but still anyway short on very high temperature application. But on top of that, and which is really the essence of the 1336, the GWP number of that product, as you can see, is about 1,000 GWP number, which is by far high, considering the objective of the European member state to go down to a kind of very low GWP below 150, if not to say lower on a long-term basis. And this is why Opteon MZ has been developed to comply with these regulations that will and are really, I would say, coming and that are coming on force in many new applications to have low GWP, zero ODP, and of course some other key elements that are considered in any application that are the flammability behavior, the of course then the efficiency that it can provide for the system. Looking at again now the details of the 1336 MZZZ isomer molecule. As you can see, I've just highlighted some numbers here on the GWP. As I said, very low GWP. It's a value of 2, which is pretty much I would say the end game for any refrigerant that can be considered, because there will be no quota on that, considering the CO2 equivalent emission that you have with that, which is pretty much null and zero. Then it's a very low toxicity product. It's a non-flammable product. and therefore also can have pretty much, I would say, no limitation in terms of where and how that product will be used, compared with some other refrigerants that are also having a low GWP, but can be a little bit more toxic or also flammable. And this is one of the good feature of this Opteon 1336 molecule. And then last but not least, when you look at the critical temperature of that product, you can see that this specific refrigerant, the 1336Z isomer, is having a critical temperature of 171 degrees C compared to the incumbent and product, that we could have been replacing at that time, which was a 245 FA, which is higher from that product. And considering that high critical temperature, you have, I would say, no limitation for the use of that refrigerant for this specific application at 160 degrees C heat supply, because there will be a pretty high, there will be no limit on the high temperature condensing that you can have for such a high temperature. So this is one of also the good reason of using and selecting this specific refrigerant for the 160 degrees C heat supply. Now I'm presenting here, again this vapor pressure curve compared with the fluid we could have been compared with, and we are still compared with, which is a 245 FA, and considering that this product is still commercial and is still used. You can understand that I would say the industry is moving from this 245 FA HFC refrigerant to a lower GWP solution, and this is where we come at play. And this is also why we have been developing and now somehow going to the commercialization of that product for such a high temperature application that the DryFiciency project has been developing and is really now presenting the benefit in terms of waste heat recovery and efficiency you can have. Back on some of the study we could have done for Fuchs in that project, you can see here, on the left-hand side, some visual expertise, we have done on the chemical stability and the temperature stability of that refrigerant in combination with the lubricant, and also next to this chemical stability we could have done on the lubricant and the refrigerant, we have done the same, looking at the temperature effect on the chemical stability of the refrigerant with the elastomers, with the other materials that could be in contact with the refrigerant, because as you can imagine, the temperature stability is very much impacted, and at least is very much dependent on the metal compatibility that you can have in these systems and complex systems. Now, in terms of high temperature stability of our refrigerant, of our molecule, we have tested it up to 250 degrees C without any I would say impact we could have seen, meaning that for this very specific application at 160 degrees C, we didn't expect, and it's been now proven that this refrigerant didn't have any change in terms of fluid characteristics. So this is again, kind of addition of what Dennis was sharing on the study. We could have done on the refrigerant that and the lubricant that Fuchs has been developing. Last but not least, and again, this was really done at the beginning of that project, but also when we were still evaluating the rationale and the reason to develop and commercialize this refrigerant. We had simulated some of the efficiency, the COP we could achieve on some systems at very high temperature, considering different conditions. And the main one that's been very much driving the adoption of that refrigerant on the market was really on the temperature lift. We can achieve with this refrigerant considering either rather low temperature lift from the heat source to the heat supply, and rather high, for our refrigerant, which is a 50 degrees C temperature lift from the heat source to the heat supply. And in a nutshell, we could say that the 50 degrees C heat temperature lift on the heat source is pretty much the limit we can expect for our refrigerant, considering the low pressure we have of this 1336 molecule. And we truly believe that if somehow in the system design we would go above the 50 degrees C temperature lift, the efficiency of the overall system is rather low, and it's been now confirmed in some application we have developed commercially. And we truly believe that this is somehow the boundaries here you have, and you can expect when you consider developing a new application such as high temperature waste heat recovery using our refrigerant. On the capacity, on the heating capacity perspective, it's pretty much the same conclusion. We know that first of all, because of the characteristic of our refrigerant, which is a low pressure refrigerant, we know that the heating capacity is on the low side, and therefore compared with the heating capacity of the 245 FA, we have to consider this specific challenge, I must say, on the system design, on the compressor design and selection, to go on good performance of the overall system. And this is why, again, in that project, Bitzer and Viking has been very much also developing good system, good compressors, to adapt with the heating capacity of our refrigerant. And this is always a combination of the lubricant, the compressor, and our refrigerant to achieve the best performance of the overall system. So last but not least, now since again that product was studied and selected for that specific DryFiciency project, so now we've come to a commercial life, and we have had some good example of the performance live of this refrigerant in waste heat recovery application. So you can see here, that now we have some application in drying sectors, industries, and we have also some newer applications that have been commercialized in the process heating and in the food industry. So this was a short overview of this specific refrigerant that has been developed and now commercial. Thank you very much.
Thank you for the presentation and your work in the DryFiciency project. The availability of a refrigerant that is capable to supply those high temperatures is really an enabler for a development like the one that we have done in the DryFiciency project. And with those two basic ingredients that we have heard already, the refrigerant and the lubricant, we will now move to the compressors. And I will hand over to Julian Pfaffel to give us some insights into the screw compressors.
Okay, thank you very much. And welcome to my presentation about screw compressor for high temperature applications developed in the DryF project. My name is Julian Pfaffel from Bitzer Kühlmaschinenbau. Just to give you a small overview what has been done during the project. On the corner right here, this is our compressor, our HS screw compressor. Mainly used for refrigeration application. And this compressor now has been adapted or adopted to match the needs of the high temperature application. So we went through all the parts. We looked at each part and checked if it's suitable for high temperature application, if it's suitable for the refrigerant and the oil combination, and if not, what would be alternative parts to substitute the parts. So First of all, we checked all the plastic materials like gaskets and O-rings, and to check the material compatibility for the refrigerant Option MZ and PAG oil, and changed then parts to fit the requirements and also to fit the high temperature on the discharge side, mainly with 140, 150 degrees C. Like pressure relief valve, check valve, shut-off valve. We went through the mechanical parts. Also, the bearings need to be changed to a high temperature version. Schrader valves, side glasses, they all not manufactured for the 140, 150 degrees C, so they also needed to be changed. On the electrical side, we need to especially change the motor. The motor here in the compressor is suction gas cooled, and we had very high suction gas temperatures, so we need a special motor here to also cope with these high temperatures. Terminal plate needs to be changed, and also some cables, motor protection devices, oil level control, etc. You can see some of the parts which have been changed here on the right side. And Dennis already talked about this, oil selection. So what was the right oil for this compressors? And in the end, we even had to change the painting to cope with the very high temperatures in the compressor. So we selected here another 2K, 2-component painting. Then we built 4 compressors. These compressors are running in the demo sites at the moment. And we took all this knowledge we gained here in this project to put it in the next generation, let's say, of compressors. We call it here CSH 2T compressor, compressor for high temperature application or dedicated for high temperature application. So all the knowledge we gained during the DryF project, a lot of those components developed during the project have now been put into this compressor, which is capable of a discharge gas temperature of 140 degrees C, and it operates with low GWP HFO high temperature refrigerants. And here we have started the first field tests now to gain more experience on this compressor series. The field test has been started with one of the EEAB members, Galen Counterflow, and that was one of the very positive parts of the project, that we directly met with possible customers, or here in this case with dryer manufacturers. We got in contact with them, and we could evaluate and start projects. Here, Galen Counterflow has built a hybrid dryer. This means the dryer can operate with gas or with a high temperature heat pump. So you can switch between gas and heat pump whenever you want. This was a very important feature for the customers, also to get this kind of technology into the market. And we have now started several field tests here for pet food and aquafeed drying in several locations all over the world. So one is in South Korea with 1200 kilowatt, another one in China with 2,400 kilowatt, and one in Norway with 3,350 kilowatt thermal capacity. And the operating point is 35 degree evaporating and 122 degree condensing. We hope now to gain more experience on these compressors and also with the applications. And then in the future, we plan to offer a complete series of or a small series of high temperature heat pump compressors based on this design. Thank you very much for the attention, and we will answer, I think, the questions after the sessions. Thank you.
Thank you very much. And it's a pleasure to see how the development in DryFiciency is moving further. This is a very positive result of the project. So I think it was a very impressive moment when the first DryFiciency compressors were delivered to our heat pump manufacturers, and now they are operating at Agrana for more than 1,200 hours. So, and it's good to see that there are more applications out there to continue that work. Thank you.
Thank you.
And with that, I would like to hand over to Søren for his presentation. Now we will move to the other type of heat pump that we are looking into in the DryFiciency project. It's the open loop heat pump and the steam compression system.
Yes, hello, and thank you, Veronica, for the kind presentation, also for the opportunity to present our company here, because I guess some of you may think, who is Rotex? We never heard of them. Yeah, looking forward to this presentation. So Rotex is an automotive company. We were founded back in the year 2000 and dates back before that. But ever since then, we have been producing automotive superchargers based on what we call centrifugal compressor. And the key element in these products is our traction drive. It's a planetary drive that can achieve quite high speeds. We have some units running up to 340,000 RPM mechanically driven. So it's quite specialized product made for automotive use, and so they are very compact and power dense in contrast to the industrial processes. We have fully in-house development and produce and market superchargers for the automotive industry and aftermarket, performance enhancement and supply worldwide. Today we have 3 product ranges, mainly our automotive superchargers used for performance, race cars and stuff like that. And then we have the new type generation compressors for hydrogen fuel cell compressors for green technology and replacing fossil fuels. And then the last one is our custom superchargers. So I guess you wonder why Rotex in this industrial process consortium. And at the time before DryFiciency started, and we were introduced by SynTef, one of our partners, as they were looking into a concept of reusing or recompressing exhaust steam and reusing it for drying processes. And at the time, there were the existing type of compressors available were screw type and piston type. They were unfortunately not able to do what's needed in this project, basically because it's a positive displacement and they cannot tolerate the high temperature that we're dealing with. And also we need a high volumetric capacity or swallow capacity because of the lower density of steam. When compressing steam, the density has so much in that role. So yeah, that's basically how we were introduced to this project, because the centrifugal compressors were deemed to be a good candidate for this. In the open loop part of this DryFiciency project, the first work package was defining the specifications. And for us as an automotive compressor, we are dealing with the airflow and pressure ratio. That's basically the primary key indicators as to what we're going to develop. So the first work package was basically defining what are we going to look into and further develop. So what was come up with was a system able of heat pumps supplying from 1 to 2 to 6 bars at the outlet. In terms of numbers that we can deal with, it's equivalent of 800 kilos per hour of steam with an inlet temperature of 110 degrees Celsius. And because we need such a high pressure ratio, at least in our terms, coming from automotive, we need a twin stage or two-stage compressor setup, where we have in serial 2 centrifugal compressors going from one stage to the next stage, and achieving the mass flow and pressure ratio required. You may wonder, the first stage is a 720 kilos per hour setup, and the exhaust or the final stage is 800 kilos, and that's because we have de-superheating. That will be more elaborated in the further webinars, but we spray water in between to cool down the exhaust steam from stage 1 to 2. So yet we still have an inlet temperature of 145 degrees for the stage 2. Yeah. When making centrifugal compressors, the design point is very critical for how the physical dimensions and how the compressor looks and designed. So each stage requires a specific impeller design and compressor design, defining also the power going through the unit. So each unit is specifically for stage 1 and stage 2. It's 2 different compressors. So our journey from automotive to industrial demands, normally we're dealing with ambient air up to 50 degrees Celsius, where DryFiciency demands nearly 300% temperature increase, along with overpressure at the inlet and also steam. And to get to the point where we could make deliverables, it was necessary to perform a lot of testing. So we have introduced several designs to come up with the deliverables for this project, which includes a lot of things, but to name a few, we simulated new compressors for each stage. We made few iterations to optimize for this process, and we have them CNC machined for each step. We are, because of the extreme inlet demands, we use a specialized hydrodynamic sealing solution. Centrifugal compressors are what you call oil-free because the lubrication and the compressor cycle is independent system separated by sealings. So obviously the sealing is a point of concern and a point of really thorough development in order to be able to handle this task. So obviously we had to use external sources to help us use the best type of sealings that we could use. We has also designed new kind of separation from our compressor to the gearbox to avoid the high temperature from the steam going into the gearbox, so we can keep it cool and within specification. We also, for system functionality, made an integrated lubrication circuit for having a more compact system for this project. So in the end, we are running compressors with a stable speed of up to 80,000 RPM, and that makes the unit very power dense and also very high efficient. And we have successfully tested the MVR compression in TRL6 together with Syntef in Trondheim, Norway. So, yeah, and to sum up, you can say Rotex is an automotive company with not much knowledge into the industrial drying processes, at least before DryF. So DryF has really introduced us to a new world. We have, through these many years of development, really identified the difficulties from going from ambient air to high temperature steam. And we have come a long way and basically made the foundation to go to a commercial solution. So basically, as mentioned before, we have our fuel cell compressors. That's one way of a carbon-free or emission-free propulsion, whereas the DryFiciency has really enlightened us and showed the path towards supercharging the drying industry for a carbon-free future. So we'll be looking forward to your questions later. So thank you.
Thank you very much for this interesting journey that you have gone along in the DryFiciency project. And we will also see results of operation in the next webinar. So please stay tuned also for that one. And now we move back to the closed loop system with the second type of compressor, the piston compressor. And therefore, I ask Geir Ropstad for his presentation.
I need to stop Søren's presentation, I think.
You can just start your screen sharing.
All right. Thanks a lot, Veronica, for the nice introduction and beginning. And thanks a lot for the opportunity to participate in this webinar. I'm here to present Heaton and Heaton's product. And I was challenged, to try to have a red thread from DryFiciency to Heaton. And that's not very difficult because we have experience, we base the development that is ongoing in Heaton on earlier experience to the DryFiciency project and to the Viking period, which Heaton comes from. So so who is Heaton? We can ask if my presentation changed. So Heaton is continuing where Viking left off. And then we added a seasoned CEO to our team, which is we are very happy to have joined. And then, of course, we connected with with collaboration partners, and then you have Heaton today. Heaton is by participating in, amongst other things, DryFiciency, it made it clear to us that the road forward, that this is a very large untapped market within the high temperature heat pump, and that the road forward is in the megawatt range. We call it our heat pump the very high temperature heat pump because it goes above the 150. I think that's gives an extra swung to the heat pump, experience has been in Europe that there is quite a large pull from the market, both directly from large international companies that require a heat pump to reach their own internal, quite tough CO2 reduction demands, but also as well from industrial equipment manufacturers that experienced companies approaching them with, also large companies approaching the equipment manufacturer with a requirement for a solution to how to save CO2. Because a lot of the large companies have been, there's been a board that takes a decision that we need to cut CO2, we need to apply it to certain regulations and so on, but there are actually, their technical department discovers there are actually no good solutions out there. So at least two of the quite large equipment manufacturers have approached us, and one of them described a little bit funny that there are people coming with their hands in the air. What shall I do about this? Can you help us? So obviously, there's a pull in the market for sure. And then from our point of view, how should you do this? Well, we are, as said before, currently scaling up the very high temperature heat pump technology platform from the Viking time into megawatt range, which we are certain is the range that we need to be in collaboration with the world's largest engine development company, AVL Strick. So here's the solution, a little bit doubled up with the information, but Heaton is building on 8 years of R&D and a very good solution, we think, within the very high heat pump is a piston-based compressor. And there's a lot of, we think, strength about piston-based compressor. And one of them is, of course, the scalability. that it's not only you don't only make a compressor, you make a compressor family very easily using the same terminology as the heavy-duty combustion engine industry. So what is then great with Heaton's compressors? Well, we both own the core technologies of the development of the piston compressor. So we have owned everything around that, and we also own the design of the actual heat pump. So we think that is a strength with Heaton, having both the compressor and the actual equipment around it to make it into a heat pump. That doesn't mean that we have to just sell a heat pump, but it means that we know and understand the heat pump, the compressor's role in the heat pump much better within a lot of internal testing and optimization. Our roadmap is that we plan to launch the megawatt heat pump at the end of 2022. And luckily for us, there are so much interest in that our few pilot versions are already sold out. I have this nice, I call it the Chinese overview with really beautiful colors on as a technical roadmap on the right-hand side. And currently we are at the very high temperature point where we are scaling up the 200 kilowatt unit to a megawatt unit in the 165 range. But in short term, we will also have heat pumps delivering above or up to and above 200 degrees C. Long term, we're aiming, because of this piston-based technology, we're aiming to have also heat pumps, what we call ultra-high temperature heat pumps, up towards the 400 degree limit. And also other variants will be produced, and we see now that because of different requirements from the customer, we might develop two-stage solutions. We might develop, but our main focus is on the scalability of the actual the piston compressor and the availability of using features like cascading and so on. That's it from me. Thanks a lot for your attention. Looking forward to questions after the session.
Thank you so much for your presentation and also that impressive roadmap that we've seen here. So there's a lot out there in the future. So this will be very interesting, I think. So we have now roughly 20 minutes of time for our virtual roundtable discussion. So I kindly ask you to switch on your videos again so that we can at least see each other, although we are quite, we're streaming from many different places. I've already seen several questions in the chat, and I think we will just start from there and see how this discussion evolves. So there are two questions for Søren concerning the steam compressor. So one about the gearbox. So have you considered a direct drive without the gearbox? As high-speed engines up to over 100,000 RPM already exist?
Basically, no, we would not consider these type of direct drives because in terms of DryFiciency, and at least just for what we are dealing with, we need at least 50 kilowatt power capacity. And a DC or whatever motor running 100,000 RPM in that size becomes very difficult to make. Our traction driver proven technology from 20 years of automotive use, and they enables us to transfer a lot of power with an electric motor and bearings that are durable enough to endure industrial demands. So no, we don't see that.
So it's a question of reliability and also scaling.
Absolutely, yeah. Because if we look at the other questions as to if we're considering producing other MVR in the size of 1 to 2 tons, we also, when we need to scale up the capacity, we need to scale up the electronic capacity. And in these types of applications, we need at least 100, 150 kilowatt capacity from the electric motors. So, again, the traction drive technology that we are making, it's scalable, so we can support. So right now, we're not considering for specific size of the heat pumps or MVR systems. DryFiciency has taught us a great deal of these type of systems and requirements. But we are going to, after DryFiciency, or actually in the remaining part of DryFiciency, improve the deliverables and also work on finding necessary sizes to offer commercial solutions. Because DryFiciency has purely been development and focusing on prototyping and proving the whole concept that's a.
Okay, thank you. So will the open loop compressors will be available as a part of your product portfolio for the future?
In the long-term future, yes.
By August, but
not by August, but yeah, it's definitely in our strategic planning to look further into this. It supports Perfect. Our vision to produce and offer products to support a emission-free future. So
okay, that's perfect. So everybody who is interested in a steam compressor, as it was demonstrated in the open loop of the DryFiciency project, please contact Søren, and he
you
all the insights on that. Okay. Oh, there are no more questions coming. That's perfect. So I will take the one on the housekeeping. The slides will be shared, and the recording will be also shared. You will find that on the DryFiciency website and also on the website of EHBA. So everything will be made available, and you can also watch this webinar again afterwards. Okay. So for then we move to the closed loop, and there are several questions for, I think we start with the refrigerant. So there's a question about the temperatures in the evaporator in relation to the high boiling temperature of 30 degrees C.
Mm-hmm. Yes, it's true that this refrigerant has pretty high boiling temperature, compared to the somehow so-called standard refrigerant that are used in the refrigeration industry. Now, the fact is that we for that specific application, but for the very high temperature heat pump application, we are not that much limited on the low side of the temperature, because we are always looking at the I would say the heat source higher than the 30 degrees C. So it's really not the challenge here, because we are always considering something higher. So that's pretty much what I can say here. We are more on the side of the 80, 90 degrees C of the heat source, and then go above that. And this is why we are not seeing it as a limit. But of course, if this would be a refrigerant that would be selected for lower temperature application, it might become a challenge indeed. It might really become a challenge. And this is why also this is really specifically designed for the kind of new heat, I would say heating source and heating application that we are developing, such as the high temperature heat pump, but also the low temperature organic Rankine cycle unit that you can also have and see for such refrigerant. I hope it's answering those questions.
Thank you. It was also a design question for the heat pump, the boiling temperature of the refrigerant, to make sure that we don't get into vacuum conditions when the heat pump is not in operation and the outside temperature is cold.
But it's really standard practice, that I would say the suppliers and the designer of the heat pump, and of course, we can be part of that. But let's say it's really standard practice, and it's never been a limit on this application.
And more challenges were to be tackled on the high temperature side than on the low temperature.
Correct.
Okay. Then we have an interesting, there's another question on the refrigerants in the project. So we had two types of refrigerant in the project. It's OptionMZ, or the DO2, as it was called before, for the closed loop, and water as a refrigerant for the open loop heat. That was already a quite complex issue to work on. And then we have an interesting question about the two different types of compressors that are used in the closed loop heat pump. So what are the pros and cons of the screw and the reciprocal compressors for different applications? Maybe Julian, could you start with that?
Yeah, that's would be a long discussion to see what are the pros and cons. But for Bitzer, we have both technologies, the reciprocating compressor and the screw compressor. And for us, the pros of the screw compressor is that we can offer higher capacities up to 1,000 kilowatt with the higher displacements of the screw compressors up to 1,000 cubic meters per hour. And this makes it for us more suitable for the industrial applications we were looking here at, because you don't have to parallelize so much compressors, while our piston compressor would only deliver maybe up to 200 kilowatts. So we would have to parallelize here much more compressors to reach the same capacity.
Okay. Geir, do you want to add on that?
I think we could have a good evening, me and Julian, and have some discussions here. But I think that the advantages with a piston engine is a lot, and but the obvious ones are the what do you call it? The flexibility. I mean, flexibility from fluid. We can use whatever fluid you give me, from the lowest temperature to DR2 or set. We could have different fluid with the exact same hardware. So the whole key for the piston is repeatability when it comes to production power. If you want to make, a 2-cylinder, a 4-cylinder, a 16-cylinder, you can make it with 90% of the same hardware. You could use the same hardware to all different working fluids, as long as you have, of course, made the as Julian mentioned, the compliant that the working fluid works with your sealing material. And of course, Viking heat engine, which Heaton is based on, their R&D manager did not choose as piston engine to start with. It was a conclusion from a study with all technologies. Then you include everything in here. So I can even go to a customer and say, do you want to have a COP focus, or you want to have an output power focus? So, yeah. For us, it's clear.
Okay. Okay, that's definitely the start of a longer discussion, but this is the different technologies are available for the different applications.
Healthy with different technologies as well. So then, because the point is that we need to get the heat pump out there. That's the most.
That's true. That's true. Okay, so I look at the chat box again. And yeah, another question for Loic. Is there a TFA problematic, or are there any breakdown products expected to be produced in the atmosphere and the environment? Very interesting question.
Yes, indeed. I'll try not to answer it briefly, because for that, I would say it's a long debate, and I really don't want to enter into that debate here. It's probably good also to take it offline, with anyone who wants also me to discuss specifically about that aspect for the refrigerant and, let's say, for our portfolio. The fact is that for that specific product, it's been studied that there is no TFA that's been I would say producing as a kind of, I would say, byproduct for this specific 1336 molecule. So I'm very comfortable to say that there is no issue on that aspect for that specific refrigerant. We have conducted a lot of studies on that specific subject for this refrigerant, and I can of course, share again offline these details, whenever it would be required, or at least whenever it's of interest for anyone.
Thank you.
Okay. But now overall, TFA is something also I can say that it's existing. I would say in the normal life, in the standard, I would say in the seawater. So again, it's very much now I would say being looked at different levels in the I would say in the industry, but also at some member state in the European Commission. But this is, of course, something that we are participating also to address it and to come to a good conclusion and probably good path forward for this industry. Okay.
Okay. Good. There's another interesting question about a two-stage setup that also picks up a bit the word that we've seen in the heat-in presentation on the variants. So in DryFiciency, we have it's a single-stage heat pump, but of course it's an interesting idea to combine the closed-loop heat pump as the first stage and to add an open-loop heat pump as the second stage to deliver higher steam pressures. And I think what we've also seen in the presentation of Julian for the new high-temperature compressor coming up, that different ranges of application are covered. So this is basically, it will be a toolbox that can be combined for whatever is needed for the industrial process. I think for the future project, it will be important to put also the needs of the industry in the center to come up with the solution that fits there. Yeah. So you want to add to this idea, to the two-stage idea? Is that a no? Is that interesting, or is it a no-go? I think so.
For me, or
whoever wants to.
Yeah, and it's definitely. So I think that is. We've had some discussions before with Mikael, or a long time ago about this, but we haven't taken it any further. But it's an interesting thought. We think that is not the best solution, but it's a solution that will work. Yeah, maybe for special applications, this is the best solution. But in general, I think it's not.
Like also mentioned an interesting aspect in the chat, cost and complexity. This is something that is always has to be taken into account.
Yeah. So if I can answer that, because that's of course I forgot to mention costs, because cost is the overall big reason that Piston is the best solution, because utilizing the enormous production facilities around the world doing heavy-duty combustion engine, which has less to do at the moment, and the whole automotive approach on production. It's not a one-off, or there's nothing else built for high volume production than a piston engine.
Okay, I will take that lead with the automotive production to take it to the next question to Søren. There's a question about, have you performed tests with inlet conditions at 110 degrees C and pressures above 1 bar, or also with pressures lower than 1 bar? And does the sealing solution prevent oil from being mixed with the steam?
Understood. Yeah. I think yes, we tested above 1 bar at SINTEF in steam. One of our challenges being automotive is that we normally deal with ambient air, so we don't have a steam test facility in-house. So all our in-house development was done in air before being shipped to SINTEF for testing in steam. And to avoid the lower density of steam creating too much power when testing in air, because the impeller is physically very large. So we had to restrict the inlet, and thereby creating a vacuum or lower B1 bar absolute. So we have tested to a pressure ratio of 3.4 under ambient conditions. So yes, we have been much far from that. And to answer the second question, sealing solution, it's actually the opposite way around, and because we're running a dry sump lubrication of the traction drive, we create vacuum inside the gearbox. So the biggest challenge is to avoid steam entering the gearbox. We can by design not have oil getting into the steam, only the other way around. So it's one of the reasons why we use it for fuel cells. Also, they're also very sensitive to oil pollution in the compressed media. So again, it's a sealing solution that really comes down to play here.
Thank you. Okay, with a glimpse to the time, when we start discussing, time flies always. Unfortunately, we will have to come to an end now. I would have a last question for Dennis on the lubricant. So we've heard there's a lot of interest in high temperature applications from the point of view of the lubricant. Are there any boundaries? Is there a development going further to exceed those 160 degrees C? So what are the challenges for the lubricant there? You're still muted.
The challenge is really the seal tube test with the refrigerants, I think, or the DR2, because we saw this total acid number increase, and it's depending on the temperature. And so I think we are able to create maybe higher temperatures, or the lubricant can withstand with higher temperatures. But I think we will need to optimize the lubricants further by a special additive system to create a stable lubricant for years.
Okay, so it's about the complete system, not the lubricant, but the mixture that we have in the heat pump.
The mixture is necessary, yes.
Yeah. Okay, thank you. And the last question goes to all of you. Coming back to the DryFiciency project, what is your most interesting or most surprising DryFiciency memory? So what is that you want to share with our audience? And maybe we start with Julian, because he's the first on my screen, and then just pass the word to the next one.
Okay, let's say from our perspective in DryFiciency, it was great to get in contact with, let's say, some kind of end users of our products, like the dryer manufacturer, where we did not have much idea about what are their requirements, what do they do, and do they want to electrify their dryers. And those discussions we had during our events then, or at the time, real life events. That was for me for the greatest moment.
Okay,
I can take it because let's say on our side, with regard to the refrigerant development, what's been really interesting and good to see with that project was really the realization of what we could have done somehow in-house by simulating in different ways, the performance we could achieve with our refrigerant. And let's say, that project, was probably one of the first we could have started to work on in terms of realization of a real system. So that was really good in that view, but also good to see how much it's complex to develop, and now finally also to see the success we can achieve on this very high, you could say probably extreme high temperature heat pump, because so far and still today it's still rare to have such a very high temperature heat pump, and good to see really the complexity and now the success of that.
Yes, our challenge was really that we are not used to create refrigeration oils or heat pump, high temperature heat pump fluids with such a high viscosity. So it's really new for us to make such a thick oil. But okay, it looks like it's working well and so on. I think the high viscosity is needed for this topic.
Yeah, I agree with all three before me, and especially Julian with the whole meeting, everybody. And DryFiciency has been a great project, given me a lot of good connections and friends, and has opened up, our eyes to a lot more information than we knew before we entered. And if I take one moment, I mean, one portion of it is the Kimor's and Fuchs collaboration regarding the oil viscosity and the degradation challenge. I think that's the most technically important outside of the rest. So technically, that collaboration and that process to get an insight to that, what was very interesting. Thanks a lot.
Okay, so Søren, you have the final word in that.
The final word is for me. Obviously we are very delighted by the eye opener for new industrial processes, and to connect with all these brilliant minded people in this project who really has helped us improve our products and also made it possible to actually prove our technology in these special extreme conditions, in our terms at least. So it's been an eye-opener. It's a completely new type of industry to deal with, in contrary to our automotive business. So yeah, it's opening doors and really open a network of new companies and partners to work with for the future of our company. So yeah.
Thank you so much. And I also want to thank you on behalf of EIT's DryFiciency team. We are almost getting a bit sentimental that the project is coming to an end now, because we really enjoyed our collaboration. It was a pleasure to realize this work together with you. And it's not only about the technology, it's also about the people. I think we are a great project team. And it's not ended yet. So in 2 weeks, we will have another webinar on the working systems. So you have heard everything about the components today, the foundation that's necessary to really build the demonstrators. And in Wednesday in 2 weeks, we will discuss the demonstrators then. I also want to thank all the participants today. Thank you for the interaction, for your questions in the chat. If you have more questions, because we overspent and still we're running out of time, you can just drop us an email and we will answer it. And we look forward to meet you again online, and maybe at some point in the future also meet you again in real life at some heat pump event. So with that, I'd like to wish you a very nice Wednesday, and I hope to see you soon. Thank you.